All right, welcome back everyone to the deep dive. You know how this works. We pick a paper, we tear it apart, we see what's inside. Today we're looking at a paper called, and get ready for it, LapSum method to differentiate them all. Ranking, sorting, and Topsy selection. Catchy title, right?
Yeah, it's a mouthful. But, I think it gets a point across. They're really trying to tackle this big problem of making these kind of like ordering operations work smoothly within a neural network.
So you're saying like when you're training a model and it needs to say pick the best 5 out of 100 options, that picking step can get messy.
Exactly. Those kind of discrete, like this one's in, this one's out decisions, they don't play nice with the way neural networks learn. Networks need these smooth, gradual changes to figure out which direction to adjust their parameters, but sorting and ranking, they create these sharp jumps. Like one tiny change in a score and boom, the whole order flips around.
And that screws up the whole learning process.
Yeah, the gradients go haywire. It's like trying to climb a hill made of Lego bricks, You need a smooth surface to get a good foothold.
Okay, so that's the challenge. Now, how does this LapSum thing, this sum of Laplace distributions, come into play?
Well, think of it this way. Instead of having a hard cutoff, like, okay, these are the top 5 and the rest don't matter, LapSum gives you a probability for each item. Like, this one has a 90% chance of being in the top 5, this one has a 30% chance, and so on. And these probabilities, they change smoothly as the network adjusts its internal scores. So you still get a ranking, but it's a soft ranking, if you will.
So instead of just saying yes or no for each item, it's more like a maybe that can be tweaked gradually.
Exactly. That's the key idea. It provides that smoothness that the network needs to learn effectively. And the authors, they lay out this whole theory of how to create these soft order operations using the sums of what they call cumulative density functions from different probability distributions.
And why is this Laplace distribution so special? I mean, there are tons of probability distributions out there, right?
Right. But the Laplace distribution, it has this amazing property. The inverse of the function they build with it, that's the LapSum part, it has what we call a closed form solution. That means you can calculate it directly without needing any iterative approximations or fancy numerical tricks.
Oh, I see. So it's like having a shortcut, a direct formula.
Exactly. No need to mess around with iterative methods or approximations. And that's a huge deal computationally, especially when you're dealing with large data sets.
Got it. So it makes things faster and easier to compute.
Yeah, exactly. And in their paper, they actually prove mathematically that this LapSum method, it can calculate all these soft order operations like the soft ranking, the soft Topsy selection, even soft permutations, all in roughly the same time it takes to just sort the data in the first place.
No way. So it's basically as efficient as just sorting. That's pretty impressive.
All right, it's big. And the memory usage, it's also super efficient. It scales linearly with the input size, which means it can handle large data sets without choking.
Okay, I'm starting to see why this could be a game changer. So they can sort of soften these operations, make them differentiable, and do it all without sacrificing speed or memory. But does it actually work in practice?
Well, that's what the experiments are for, right?
Right. So let's dive into those. What kind of tasks did they test this LapSum thing on?
Well, they started with image classification. They trained networks on CIFAR-100 and even some ImageNet data sets, focusing on how well the networks could predict the top 1 or top 5 most likely image categories.
Classic image classification.
Yeah.
So how'd LapSum do?
Really well. I mean, they found that it either beat the pants off existing differentiable Topsy methods or at least performed on par with them, especially when dealing with high-dimensional data like these image features.
And it didn't need any special hand-holding.
Nope. Like some methods need you to tell them up front how many top items you're interested in. But LapSum's approach to differential ranking, it just worked no matter how many top items you wanted to pick.
That's pretty flexible.
Yeah, totally. And they also did all this analysis on runtime and memory usage, comparing LapSum to all these other methods. And the results were pretty clear. LapSum was way more memory efficient, especially with bigger data sets.
So it's memory friendly? Got it. What about speed?
Speed was also great. It was either faster or at least as fast as the other top methods, both on CPUs and GPUs, which is important for practicality. They even ran some statistical tests to be extra sure that these performance differences were legit, statistically significant.
Okay, so it's fast, it's efficient. What about that softness parameter they mentioned, the alpha?
Oh, right, alpha. Yeah, they did a bunch of experiments with that too. They showed that by letting the network actually learn this alpha parameter during training, it could kind of figure out the right level of softness it needed for the best performance.
So it's like the network's getting to fine-tune the method itself.
Exactly. And that seems to be one of the secrets to LapSum's success. It's got this adaptability built in.
Clever. Did they try it on anything else besides image classification?
Yeah, they also tried it on a k-nearest neighbors, KNN, task, which is a totally different type of problem. And again, using LapSum's soft top K selection didn't hurt the performance at all. So it seems pretty robust.
Interesting. So it can generalize to different types of tasks?
Yeah, it looks like it. And they even applied it to this permutation learning problem, where you're trying to learn how to rearrange a set of items. And once again, LapSum did really well without needing any fancy modifications to the model.
Okay, so it seems like they've really put this method through its paces, and it's held up pretty well. It's fast, it's efficient, it's accurate, it's adaptable. But I guess the big question is, so what? Why should we care about this LapSum thing?
Right, let's zoom out a bit. Think about the history of machine learning. Sorting and selection, those are like the bread and butter of computer science. But for a long time, they've been this big pain point in neural networks.
Because they're not differentiable.
Exactly. And neural networks, they thrive on differentiability. So researchers have had to come up with all sorts of clever workarounds to incorporate these operations indirectly. This paper, it kind of feels like a turning point. They've found this really elegant and principled way to make these operations differentiable without all the usual compromises.
And it fits into this broader trend of making more and more things differentiable within machine learning.
Yeah, it's all about building these end-to-end trainable systems that can handle more and more complex tasks. And the real magic here is that they've done it using this Laplace distribution, which provides that crucial closed-form solution for the inverse. It's like they've unlocked a hidden door that nobody knew was there.
So if I had to sum it up in like a tweet, what would you say is the key takeaway from this paper?
Tough one. How about this? LapSum, a new way to sort and rank within neural networks. Fast, efficient, and it actually works. Get the code, play with it.
Perfect. Okay, it's time for our Novel Notions segment, where we let our imaginations run wild for a bit and brainstorm some potential future directions based on this paper.
All right, hit me.
Well, LapSum is all about making top teen selection differentiable, right? And that got me thinking about reinforcement learning, or RL.
Okay, I see where you're going with this.
In RL, you often have these agents that need to choose an action from a set of possible actions. And a lot of times they're trying to pick the best action, or at least a few of the best actions. So why not use LapSum for that?
Interesting. So instead of having the agent just pick one specific action, you'd have it use LapSum to create a probability distribution over the top king actions.
Exactly. And those probabilities could change smoothly as the agent learns. It's like giving the agent a bit more flexibility in its decision-making.
That makes sense. And because LapSum is differentiable, the agent could directly learn from the consequences of those probabilistic action choices. The gradient signal could flow all the way back, guiding the agent to improve its policy.
Right. And maybe this could lead to more stable learning, too. Instead of the agent jumping between a few discrete actions, it'd have this smoother exploration process.
Yeah, maybe it could even help the agent avoid getting stuck in those local optima traps that RL is so prone to.
I like it. And think of the applications. Robots learning complex motor skills, agents making decisions in dynamic environments, all sorts of things.
Lots of potential there. Of course, this is all just speculation. We'd need to do some experiments to see if it actually works.
Of course, of course. But that's the fun of research, right? Exploring these new ideas.
Absolutely.
Well, I think that's a great place to wrap up our deep dive into LapSum. It's a really exciting paper, and I'm eager to see what kind of impact it has on the field.
Me too. It's definitely one to watch.
And as always, you can find a link to the paper in the show notes. Thanks for listening.
See you next time.